Welcome to our seminar on solving the IoT power consumption measurement challenges. I am Robert Green, a product marketer at Keithley Instruments, and I will be your presenter. The objective of this seminar is to help you address the challenges of determining how much power your product consumes and of assessing battery life. Examples of the types of IoT devices you are designing now and in the future will be wearable devices, portable medical devices, and battery-operated industrial sensor transmitters. For these devices, maximizing battery life is essential. To meet the design requirements for battery life, the designer needs to be able to determine the total power consumption that the device is drawing. That means selecting low power components and being able to measure the very low currents that your product will draw. You also need to account for the fact that your power source is a battery, a source whose characteristics are changing as your product is operating. We will review the measurement and test challenges and offer our suggestions and our solution. Let's get started. This graphic illustrates the expanding universe of the Internet of Things and how this will affect all aspects of our lives. Interconnected appliances will include everything from the consumer goods we are familiar with to healthcare products, building management products, transportation products, and a wide range of industrial products. Prognosticators expect double-digit growth rates in industrial IoT products with various market segments growing into the tens of billions of dollars. This chart does not even show a segment for agriculture. One forecaster projects that agricultural IoT products will boost food production 70% by 2050. Of course, there will be numerous other areas that we have not even thought about. With such a vast array of markets and products, it will be very unlikely that a few companies will dominate this total market. That means plenty of opportunity for all of you. This plot illustrates the projected growth in IoT products and compares it with the global population. Just looking at the consumer goods listed on the left of the chart indicate how all of us already have multiple connected devices. The expectation is that there will be 25 billion connected devices by 2025. Will that be a low projection? Let's get to your challenge. You have got to squeeze your product's power consumption as low as you can get it so you can maximize battery life. That means you need test tools to perform a number of functions. That includes qualifying critical low power components. Once you've chosen your components and assembled your design, you need to be able to measure the power consumed in all the operating states of your device. That includes the low power sleep mode, standby modes, and the short pulsatile RF transmission modes. You have or will select a battery. The battery certainly impacts how long the device will operate before the battery must be replaced or recharged. One important need is to determine your product's low battery shutoff voltage. If you choose too high a voltage, you will lose some operating life. I do not envy you. For low-power devices that must operate a long time on one battery discharge cycle, you are not given a lot of power to work with. In this example, you have a power budget of only 80 microwatts. Here is an example of how the power might be allocated for a Bluetooth low-energy sensing product. These are minuscule power levels. As shown in the upper right, if you are using a 4-volt lithium-based battery, your product's average current has to be a tiny 20 microamps. To achieve or exceed your power budget, you need to optimize your design, and that means you need low power components. Fortunately, very low power components are available. Here are some example operating currents from components that have been introduced in recent years. For example, low-power op-amps on the market now operate with 1 microamp current draw. Even the microprocessor manufacturers are targeting this market with low-power products. The muscle spec for a microprocessor has always been higher operating speed, gigahertz clock rates. Now for low power, the suppliers are offering a power versus speed trade-off with ultra-low sleep mode currents. Note that many of these components have ultra-low currents in the hundreds of nanoamps range. For those components that are critical to your design, you may want to characterize their performance. What is the current draw at the voltage you will be using? How does the current draw change as your battery voltage decreases? Is there a range of voltages where the efficiency decreases significantly? This can be the case when a component is operating at the low end of its specified operating range. A component may behave as shown in the IV plot in the upper right. You have got to be able to measure microamp and nanoamp current levels. These are levels you normally have not encountered in the past, and measuring these levels requires sensitive instrumentation. An instrument that can both source voltage and measure very low currents is a source meter instrument, or an SMU. They are versatile instruments. SMUs are bipolar voltage sources, bipolar current sources, and they can be electronic loads. They have excellent low current measurement capability. An SMU tightly integrates sourcing and measurement so current voltage plots can be easily created. The upper left shows a block diagram of an SMU, and the lower left shows one of the Keithley SMUs. We have an extensive line of these instruments. I would recommend you consider a source meter for your design team. Component currents are only going to get lower. Now that you have selected your components and built your prototype, you need to determine its power consumption. There are challenges to accomplishing that task. You need to measure the load current in all your product's operating states, illustrated in the simplified plot shown on the lower right. That entails measuring the low sleep mode current and the active mode currents. Sleep modes, depending on product complexity, can range from extremely low tens or hundreds of nanoamps to tens of microamps. At the other extreme, the maximum load currents will occur when your product is transmitting, and those currents can range up into the amps levels. Thus, current measurements need to be made over a very wide dynamic range. In addition, during the transmission state, the load can be short current bursts from microseconds to milliseconds. For estimating battery life, you will want to capture a profile of the load current that simulates a typical usage profile. Also, the more detail you have on the load current profile, the better the chance you can capture unwanted events like transients. For example, an uncontrolled transient in a DC-DC converter will consume extra power and reduce battery life. To summarize, to measure these load currents, you will need sensitivity, dynamic range, speed, and reading storage depth. In reality, the load current states are not as simple as that shown in the previous illustration of the product operating states. The center plot shows a current profile from a low-power IoT device, and the bottom plot shows the detail of a current draw from a low-energy Bluetooth transmission. If you look at the details of the center plot, you will see very low currents, ranging from 70 nanoamps to 29 milliamps. You will see 4 millisecond pulse widths. With an in-depth understanding of your load current, you can see how much current each operating state is consuming. That can help uncover problems or suggest ways to revise your control code to possibly keep some components in lower power states or de-energized for longer periods of time. A plot may uncover an unexpected and unwanted current draw, such as the spike shown on the lower plot. If that is a transient, can a hardware modification or a firmware modification eliminate or reduce it to eliminate the power it consumes? The more accurately you can capture your load current profile, the more valuable information you have. To capture all the aspects of your load current, which to repeat can be complex wave shapes, as shown in the two plots on the right, you need the following measuring capabilities. 0.1 nanoamp sensitivity if you have a deep sleep mode with just your controller and a few components that need to be operational, your instrumentation needs sufficient accuracy to trust what you are measuring. For the active state RF transmission modes, you need the bandwidth and sampling rate to capture the current bursts. To obtain what you want to analyze, you need triggering options, particularly if you need to correlate a specific current with controller actions. The ease with which you can display waveforms and waveform data helps your analysis. Furthermore, having a deep memory enables collecting operating profiles. I wanted to remind you that the act of making a measurement on a circuit or on the complete product most often causes a disturbance. Measuring current typically adds a voltage burden to the circuit, which reduces accuracy. Current measurement instruments use one of two topologies to measure current, the shunt ammeter or the feedback ammeter circuit. The shunt technique puts a resistor in the circuit and measures current by dividing voltage across a known shunt resistor. The shunt resistor has to be large enough to create a voltage that the instrument can accurately measure. A typical 6.5 digit DMM, a good quality DMM for example, can add voltage burdens of 150 millivolts to 1 volt to a circuit. If you are using a battery with a voltage of 4 volts or less, the voltage burden can reduce the circuit voltage by 7% or more. That is a lot of error added to the measurement uncertainty, and the signal-to-noise ratio is also reduced. In general, the shunt ammeter topology limits sensitivity. The feedback ammeter topology uses an op-amp current-to-voltage converter. Since the input voltage across an op-amp is negligible, the voltage burden seen by the test circuit is extremely small. The current builds up a voltage in the feedback circuit, and the feedback resistor can be a very large value since it does not impact the measuring circuit. That allows ultra-low current sensitivity. Instruments using the feedback ammeter technique can get down to femtoamp, 10 to the minus 15th amp sensitivities, and signal to noise is not degraded. The limitation with the feedback ammeter technique is bandwidth. Feedback ammeters tend to be used in low-frequency current measurement instrumentation. For bandwidth, the shunt ammeter topology has the advantage. Now that we know what we need and are aware of some of the issues with current measurement, let's take a look at our instrument alternatives. Here is our test circuit for load current measurement with a voltage source, supplying the load current to the device under test. I brought up the impact of voltage burden related to inserting a measurement instrument into a circuit for current measurement, but I did not mention that current can be measured without disturbing the circuit at all. Current probes can detect current by surrounding a wire with a Hall effect detector and not having to insert anything in the test circuit. That would be an ideal answer. Oscilloscopes with current probes can capture all the details of a current burst. Depending on how much you want to invest in a scope, you can get bandwidths well into the gigahertz range these days. That is more than enough. Scopes have plenty of memory and numerous triggering methods. But our ideal instrument fails to help us with the low sleep currents. Current probes are generally limited to milliamp levels, insufficient for sleep mode currents in the nanoamp ranges. The scope with a current probe solves one part of the measurement problem, but not both. Let's take advantage of the oscilloscope's signal capture capability and put a sense resistor in the circuit. Again, oscilloscopes are designed for fast sampling and wide bandwidth. Their resolution is limited, typically only 12 bits or less. The trade-off is low sensitivity, typically millivolt sensitivity. You would need a good-sized resistor for the sleep mode currents. When measuring the active state, such as the RF transmit, the voltage drop caused by the sense resistor will have a large impact on the voltage that powers the device under test. For example, a 10 ohm sense resistor with a 100 milliamp peak current flowing would cause a 1 volt drop. The DUT would see a 25% voltage reduction if it was intended to be powered by 4 volts. Scopes are just not designed to be sensitive measurement instruments. Let's consider two low current measurement instruments and see which requirements they meet and show up as green in our table of needs. A picoammeter and a source meter use the feedback ammeter topology. They solve the sleep mode measurement problem with minimal voltage burden and more than enough current sensitivity. Voltage burden on Keithley picoammeters and source meters is specified to be below 200 microvolts. However, these meters are primarily DC instruments. They cannot help to acquire the active mode current bursts. We still have solved only one part of our multi-part measurement challenge. Let's look at a good quality DMM measuring voltage. Alas, DMMs are great general measurement tools, but they lack the performance we need. For sleep mode currents, you need a good sized resistor to build up a large enough voltage for the DMM to detect. For example, a 100 nanoamp sleep mode current across a 10 ohm resistor builds up only 1 microvolt. Again, when measuring the peak current burst, the sense resistor will cause a significant voltage drop in the circuit. DMMs typically do not have high sampling rates. 50 kilohertz is fast for a DMM, nor do they have wide bandwidth or large data storage banks. A typical DMM cannot solve any of the measurement challenges. Using a DMM in the current measurement mode does not offer any advantages over the voltage mode. Neither the voltage nor the current function of a DMM adequately address the measurement challenges. Fortunately, Keithley has concentrated on the IoT power measurement challenges and provided an instrument that can meet the requirements for high sensitivity, fast sampling, and deep memory. The DMM 7510 can measure sleep mode current with 1 picoamp sensitivity. Using a unique hybrid shunt ammeter feedback ammeter circuit, the DMM 7510 can measure low currents with a very small 15 millivolt voltage burden. To capture the fast current burst due to an RF transmission, the DMM 7510 can sample at rates up to 1 megasample per second. The DMM 7510 has numerous trigger options to initiate the capture of a current burst. The instrument also has a deep memory for capturing a profile of all the operating states of your product. In addition to displaying numerical readings, the DMM 7510 has a touch screen graphical display. Waveforms can be plotted, and a pinch and zoom capability allows detailed analysis of a waveform. Thus, you can expand and study the load current bursts in great detail. Let me give you a feel for how good a sleep mode measurement you can make. On the DMM 7510's lowest current range, the 10 microamp range, the DC current accuracy is 75 ppm of reading plus 30 ppm of range. A 1 microamp reading shows digits down to 1 picoamp with a 0.375 nanoamp tolerance. The accuracy specification covers a 2-year time interval. Thus, this measurement quality is not limited to a very short time period. For current burst captures, the measurement can be triggered by a level on a rising or falling edge, the occurrence of a pulse, or a value within a specified range. Bus triggers and external signal triggers can also be used. In addition to pinch and zoom manipulation of waveform data, you can use cursors to make computations and compute statistics on the data. You can also combine numerical and graphical data on the display. The DMM 7510 provides all the capability you need to meet the challenge of making power consumption measurements. Now you need to consider how the battery affects product performance. The battery is not a well-behaved constant voltage source. Battery voltage decreases as it discharges. The rate of discharge varies depending on the current draw, as shown by the battery discharge curves on the top right graph. The 4 curves show battery discharge characteristics of an AAA battery based on 4 different current levels. Note that the plot for the lowest current shown is 50 milliamps. That is much higher than the average current your product will draw. To compound the problem, the internal resistance of the battery increases as the battery discharge cycle progresses. That is illustrated with the red plot on the lower right graph. You will want to test your product at various voltages. It would be nice to have an efficient, repeatable method for emulating the battery voltage. We will model the battery as an ideal voltage source with an internal resistance as shown on the left. So when your product transmits a signal and draws the maximum current output for a short period of time, the battery voltage will drop by a voltage equal to the current change times the internal resistance. The battery terminal voltage at any time will be the open circuit voltage less the product of the load current and the internal resistance. Both the open circuit voltage and the internal resistance are varying with time. You will want to know how low your battery terminal voltage can go and how low the added voltage drop due to the product of the current change and the internal resistance will be, so you can determine your optimum low battery shutoff voltage. You do not want your product to shut off during a transmission, which could happen if the drop due to the current rise puts the terminal voltage below the shutoff level for a long enough time for your low battery circuit to activate a shutdown. And you do not want to set your shutoff level too high because that reduces battery lifetime. To find the optimal shutoff point, you need to understand the characteristics of your battery. A solution is a battery simulator. A battery simulator is a special function power supply that can model both a decreasing output voltage and an increasing output resistance. Thus, a battery's open circuit voltage and its internal resistance can be programmed to represent the state of a battery at any point in time. The third major feature of these supplies is their fast transient response. The fast response enables the supply to emulate a battery's ability to respond almost instantaneously to a load current change. Using a battery simulator, you can emulate a battery's internal resistance with a programmable output resistance, and you can emulate the battery's open circuit voltage with the simulator's variable voltage output. But how do these values change as the battery discharges? The plot on the bottom shows how a lithium-ion coin cell battery's open circuit voltage changes with the battery's state of charge. A lithium-ion battery holds its voltage until near the end of discharge. Then the voltage falls off quickly. The plot on the right shows how that battery's internal resistance increases substantially as the battery nears end of life. Is there a way this dependence with the discharge cycle can be accounted for? The answer is yes, and Keithley does it with their Model 2281 dynamic battery simulator. This battery simulator includes a model of open circuit voltage and internal resistance, or equivalent series resistance, as a function of state of charge. For each integral state of charge from 0% fully discharged to 100% fully charged, the simulator outputs a unique voltage and programs a unique output resistance. The state of charge is equivalent to the amp hour capacity of the battery. As the battery simulator supplies current, it computes the amp hour product representing battery capacity consumed and changes the output open circuit voltage and internal resistance based on the model. So how can you create a model? Well, you need an algorithm, and that algorithm has to monitor battery voltage and compute the battery's internal resistance as the battery discharges. You want to create the discharge plots for your battery similar to the CR2032 coin cell discharge plots shown here. Of most importance, you want the model to be relevant to the product you are designing. Thus, you would like a model that is based on the current that your product will draw from the battery. The solution to the model creation problem is to use the Keithley Series 2450 source meter as a load. The SMU can sink a constant current. Due to its low current sensitivity, it can sink very low currents, even currents below a microamp. Keithley has created a model generating program that can be downloaded into the Series 2450 SMU. The SMU will discharge the battery, take the necessary measurements, and create a model in the format required by the 2281 battery simulator. The model generating program monitors battery voltage, creates a momentary delta voltage to force a delta current to compute internal resistance, and monitors current and time to compute amp hour capacity. The program has a number of programmable parameters, and the main one is the discharge current. The program creates the battery model consisting of 101 sets of 3 parameters: state of charge, open circuit voltage, and internal resistance. The 2281 can enable you to quickly simulate any point on the battery discharge curve. For example, you can set a low VOC to test your product when the battery is near the end of its discharge cycle, or you can test at a specified state of charge. The other parameters are adjusted based on the model. You can program the simulator output to any point on the discharge curve quickly and repeatably. You cannot do that with an actual battery. The unique display shows all the battery parameters and graphically shows the state of the battery. You can store multiple models in the battery simulator so that you compare the performance of different batteries during development. You have measured your product's load current, and you have determined an average value. You can then estimate battery life based on the battery manufacturer's capacity specification. Or, if you've used a battery simulator and have captured the load current in every operating state, you can determine a more accurate battery life. You can source your product with a simulated battery discharge curve based on the average current draw for your product. You can discharge the battery down to the shutoff voltage you have established, and you can cycle your product through a usage profile. The discharge time will be based on the most realistic conditions that you can establish. While this discussion is focused on the DC power consumption test challenges, Tektronix and Keithley can offer a complete set of test and measurement solutions for all the circuit blocks of your product. For DC power consumption, we have shown how the DMM 7510 graphical sampling multimeter has the sensitivity, speed, and memory depth to capture your product's power consumption in all its operating states. The 2281 battery simulator dynamically simulates your battery with a battery model and enables you to efficiently and repeatably test at any point on the battery model. The Series 2450 source meters both can help qualify low power components and create battery models. These 3 instruments solve your power consumption measurement challenges. Be aware that we offer excellent solutions for testing the RF blocks of your IoT device. Tech offers the MDO series of oscilloscopes with correlated time and frequency domain measurements. The RSA series instruments are compact real-time spectrum analyzers. SignalView software provides vector signal analysis and wireless modulation protocol analysis. Vector signal RF sourcing is provided by the TSG series signal generators. Tech and Keithley can help you with all your IoT product measurement challenges. Thank you for attending this presentation. For more information, visit our website or contact me directly at the email address shown.